and this happens. It doesn't affect me. It affects you. What we see is a bug in the linked list because it's written something over top of something else in your code. And now people are after you, and it's my fault, and they can't catch me. Because how would you even know it was me? You know, it's the beauty. Depends how you look at it, or the horror of the end point. So the problem here is illustrated for that complicated example here, where I now have at step 2, bar has a pointer to something that's been allocated. And foo does, and then bar saves this in a global variable. So A and B is here, it's a global variable. And then I come back to foo, and if I free it, A and B is a thing, and that will show up at some point as something bad. So now it's pointing right into the middle of some other data structure. It's pointing to memory that it's free. Shouldn't have been free, but it was free. Just go to the other way. Right, so here's that thing that was just allocated. Eventually we save it in a global variable. And then we call free. It's no longer allocated. And then, free is called in something else, and now something else is allocated later. This pointer now is pointing in the middle of something else. That's the purple thing. And if I use it, I've just written a 0, in this case, into the middle of some other data structure. And it's really bad. This slide, I'll just do this one, and I'll show you an example. This just illustrates what's happening. Before the free, everything's good. After the free, everything looks the same. But this now could be reused, and then step 3 it is reused. And something else is there, even though the pointer still points to this whole place. So here is the program, and it implements a singly linked list. So there is the struct linked list node. The values in the linked list are integers, and then there's a next pointer. There's a head pointer that points to the beginning of the list, and then some mysterious. So everything you see starting with bad, you have to picture that's my orange code. And you wrote, I simplified it for you. You wrote a singly linked list. That's your code. So first look at good. Good is your code. So we make one element of the list. So I allocate an element to the list. I'm going to print out what the head pointer is, store 100 as the value, set the next pointer to null. And then I have the recursive traversal of the list to print out the value. So what I'm going to do is I'll say, here I am, and print out the address of the linked list element node, and then print out the value. So that would be 100, and then call it recursive. And then what I do is I say make good, good print, good print. And what happens is that's the address of the thing that was allocated. And then so remember that here I am. The first thing that the printer prints, it's the head, prints out the value in the head. 64 is, in hacks, is what? That's 100. And then I do it again. And So this is like your unit test code. Now, of course, you would have tested it with more than one thing in the linked list, but the error is illustrated perfectly fine with just this stuff here. Now here's the bad code is what I wrote. So here, and they're in the same file, but you gotta imagine this is a completely separate, like a really big program, some file you've never seen before, maybe in a library. You never even use linking, you've never seen it or could see the source code. So what bad does is it allocates something and then frees it. Okay, so now bad, global variable is a dangling pointer. And then bad step 2 does, you'll see on Wednesday what this string n copy is. We're going to copy as an example of two best practices. Avoiding this problem, so string n copy, what it does is it copies a string from one location to another. So it will copy this string, ABC through 0 through O, into the memory that bad is pointing to. So I'm using a dangling pointer, and I'm writing into the memory that it points to. So what do you think is going to happen? Something bad. Right? Because I have head. Which points to an object that's supposed to be 0x64 and null. And then I have bad, which I'm not really sure where it points. But it's a dangling pointer, and then I've written into it the string A, B, C, O. So I've written that string somewhere in memory. And now we'll compile this again, and run it. And there it is. Segmentation. I love the segmentation. Why? What do you do when you get a segmentation? Cry. Okay, well, what's the cry? What's the next thing you do? Okay, no. It's something much easier. Maybe eventually you algorithm, but that's like real desperation. What did I just do? What is minus G? You know? Yeah, so this now lets me run GDB and see symbols, line numbers, variable names. So I just compile it like that. Now, it didn't change anything, but now I can run this to GDB. Well, and this is why I love segmentation. Because running it through the debugger gets control right at the point you get the segmentation fault, rather than your program crashing. So to show you right where it is, you see there's a line, it's right there. That's what happened. The error was that when I dereferenced node, in a call good print alpha, that address was an illegal address. Now the question is your fault or somebody else's. So you're the one who wrote the list code, you tested it thoroughly, and now I'm coming to you and I'm saying the customer's reporting that your code is not working. I have proof. It's not working. Now, the question is, what's actually happening? I'm going to push the code back up here. So you see the symptom, right? The symptom is, so here's, maybe it would be helpful to know that, remember that good health printer is recursive. So we don't actually know which recursive step we're in. Now you can see that by doing So that's showing me what's called a stack. So this says, okay, main started, main called good print, it called good print helper, and it called good print helper. So we're in the second recursive, the first recursive call. So what happened was called good print called good print helper. It printed once. This is, then it calls with this. Now now in the recursive call, in the recursive call, node is node arrow next. So when I'm getting the error, node is that value. It should be null, and if it's null, that ends the recursion. But somehow it's not. Everybody's good with the syntax? Okay, so now take a look at the code. Make sure we probably show it. Like that. Bad, remember, is a local variable. Okay. Discuss this for a minute. What happened? Or, just as good an answer is, what would you do next in debugging this? Okay, so does anybody think they know what happened? Well, what would you do next in debug this? You're just ready. Follow the nodes back. So let's go into the debugger here. I can print out any variables I want. So let me print out bad and head. Notice anything interesting about bad and head? They're the same. So what that means is that bad, it's the same thing we saw earlier with the integer here. Bad and head are both pointing to the same spot. So the problem here is that I called bad step 1 before I called make good. So what it did was it allocated bad here. And then it freed it. And then I called good, and your code ran, and it grabbed a piece of available memory. But I have a pointer to it. So now they're both pointing there. And then in that step 2, I copy a string into it. And you can also see this. So another thing, and you said something like, follow the pointers. Well, I know that node is the error. So what if I print node? Now what is that? Well, you'll notice there's a pattern. 0, 0, and then 6F, 6E, 6D, 6C, 6D, 6A, 6'9". What do you think that is?
Is that the string?
That's the string. Yeah, that's A, B, C, D, and then the 0 at the end of the string. I mean, we're not seeing all of it, some of the string right here. Why is it in reverse? Why? Because I wrote, the string I wrote was A, B, C, D, E, but it's coming out in reverse. Why is it coming out in reverse? Little endian, yeah, exactly. The little n, the lowest address is 69. So what happened was I wrote the string over this, corrupting that pointer, and then I did that code. Good code, perfectly fine, no bugs. Then you traverse the list and you have a corrupted pointer. Now, this actually was not so bad because I got a segmentation fault. You eventually with dangling pointers you do get a segmentation fault, but the key thing to observe here is you don't, like I didn't get it. You got it. Code that has no bugs is seeing the symbol. Does that make sense? So what we're going to do next class is we're going to look at some best practices for how you can avoid these errors. And then going into Friday, we'll look at the complicated cases for those best practices. Yes, I will post this code to the